Okay. Hello everyone. Suppose if we are asked about queuing models, I mean, what are all the factors or what are all the things that rule a queuing model if you are asked to find out? What are the important points that need to be discussed is what I will be talking about in this video. Okay. What are the elements or the parameters of a queuing system? First, we will talk about that so that we have a clarity on queuing system. Elements or parameters of a queuing system. Yeah. Those who are already aware of a queuing model, the Kendall's notation and all that, or normally any layman, if you are asked to describe about a queue, they will say that there will be some arrivals. There will be some people who will be standing in the queue. There will be some people who will be leaving the queue either after getting the service done for which they are waiting in the queue, or randomly just because they have some other works, they have left the queue, kind of things. Of course, this is all about human queues or population queues I'm talking about. Of course, again, we can talk about mm, cars or railway, trains, or any other things that are waiting for service. Those are also come under the queue only. Okay. Yeah. So let me discuss about what are the elements that are there in the queue. First thing would be the arrival pattern or input. You have to give some input now. So input kind of thing is our arrival pattern of the queue. Okay, arrival pattern. Usually we assume that customers arrive at random and just join the queue. Usually we assume that assumption. There will be definitely some assumption that customers arrive at the queue randomly. Okay, and join the queue. Join the queue. Okay. So what exactly we will calculate is per unit time, per hour or per 8 hours, something like that. Per unit time, we'll calculate how many arrivals are there. Okay. So the average number of arrivals, usually we denote by lambda. Lambda is nothing but number of arrivals per unit time. It depends on how you're fixing your unit time, whether it is 1 hour or whether it is half an hour, all those things are up to you. How do we fix it? Okay, so lambda is anyways, we know lambda, we have seen it in exponential distribution. Okay, so lambda is nothing but the averaging parameter, average number of arrivals. Average number of arrivals are denoted by lambda. Okay, now usually we assume though they arrive randomly, since lambda is the averaging parameter and it is related to Poisson distribution, the people who proposed queuing theory have assumed that arrivals are Poisson in nature. Okay, we assume that arrivals are Poisson in nature. Okay, yeah. So what happens is Pn, probability of n arrivals, would be given by lambda power n e power minus lambda by n factorial. Poisson, when Poisson comes into picture, we know the formula for Poisson, of course. Okay, yeah. Along with arrival pattern, there is also one more thing that we need to consider. That is the inter-arrival pattern. Usually, if you see in a queue, it is not that all the people have assembled and then the queue is going on and on, people getting served like that. There are in between some arrivals as well, which would be called inter-arrival, which we call it as inter-arrival time. There's something called inter-arrival arrival time. This also has to be taken care of. Okay. Yeah. One of the parameter for a queuing system would be inter-arrival time. What exactly is inter-arrival time is the time between two successive arrivals. Time between two successive arrivals. Okay. If there are, if the number of arrivals are, we have assumed them to follow Poisson distribution, then the inter-arrival time follows negative exponential distribution is the assumption. Usually, exponential power negative power is usually considered because exponential function is infinitely increasing function. Only if there is a negative sign in the power of exponential function, e in the power of e, only then we are assured that the value finally that we are obtaining will be converging. That's the reason Poisson, if you observe also, e power negative lambda is there. If I would have had e power positive lambda, then I cannot assure that the term, whatever is there, Pn or whatever, probability of n arrivals or Poisson distribution, probability distribution function, I cannot assure the convergence of the probability distribution function in short. Okay. Okay. The time between two successive arrivals is called inter-arrival time. Okay. Yeah. So here the basic assumption, the important one that you need to remember is if number of arrivals follow Poisson distribution, then inter-arrivals follow negative exponential distribution. Negative exponential. I'm using P dot D for Poisson. Okay. Yeah. So how do I write that? Negative exponential distribution. How do I write that? F of x is equal to probability that inter-arrival time is inter-arrival time is t units. Okay. So f of x is lambda e power. We know exponential distribution as well, guys. Okay. Exponential distribution is lambda e power lambda t. But then here we have assumed that the inter-arrivals follow negative exponential distribution. Hence e power negative lambda t is there. And t ranges from 0 to infinity. Even e power negative infinity tends to 0. Okay. Yeah. Now you see how the inter-arrivals are distributed. Let me show once. How inter-arrival time is can be split. Just see here. Inter-arrival time between 0 and infinity. See, suppose if I am dividing it into two parts. Okay. Then what happens is it will be something like 0 comma t and t comma infinity. Okay. That is what. Suppose there are no arrivals. No arrivals in time t. Okay. And one arrival in time t comma infinite. Of course, I should not say t here. 0 to t interval. There are no arrivals. There is only one arrival. Suppose if I am assuming like that, then how things will change? Let us see. See how I'll calculate probability. Probability that one arrival after time t, okay, That is what? Till time t, there is no arrival. That is probability that there is no arrival in time t. That is given by 0 to t lambda e power minus lambda t dt lambda. I'll integrate e power minus lambda t. So I'll have something like this from the limit 0 to t. I'm sorry, this is not infinity. This is t. Hence, I'll land up with e power minus lambda t. These two will go off. Okay, yeah. Now you see, let us assume that the probability that no arrival in time delta t is equal to e power minus lambda delta t. Okay, yeah. So suppose if I expand e power minus lambda delta t, what happens? Expanding expanding e power minus lambda delta t. What do I get? Like as e power minus x. If I'm expanding, what I'll get will be 1. Of course, e power x only, let's assume, which is easy. Instead, I'll insert this minus inside this bracket. Okay. Where for all the even terms, it's positive. And for all the odd terms, it is negative. And so on. It goes on and on. I'll write here e power x expansion kind. Okay, now what happens? Delta t is already small. Something like, suppose if delta t is 0.01, squaring it, cubing it makes it even more smaller. Hence, we neglect the higher order terms of delta t, neglecting higher order terms delta t of delta t. Okay, what happens is, what I'll be left with is probability that no arrival in time delta t is equal to 1 minus lambda delta t. Okay. Probability that one arrival in time delta t is given by lambda delta t. If there is one arrival, then it will be lambda delta t. Okay. Okay. So finally, what I will say is, how do I find out inter-arrival time? This is how I will do it. Okay. Since exponential distribution is a continuous distribution, I'm considering negative exponential distribution, which is again a continuous distribution. To find anything, I need to integrate. As you know, discrete distributions where I need to summate, I need to take the summation. When it comes to continuous, I need to take the integration. Hence, I have taken the integration to estimate the inter-arrival time in the interval 0 to infinity or 0 to t and t to infinity kind. Okay. Yeah. That is what inter-arrival time is one parameter of queuing system. Okay. Now coming to the third parameter, that would be service. How much time? Service time. How much time each, the system or a person is taking to serve the one who is in the queue, that would be called the service time. Okay. Yeah. This can be, service time can be a constant or it can vary. A constant or it can be a random variable. Okay. Okay. Now you see, probability service time distributions are negative exponential distributions and Erlangen distributions. Okay. What we assume here is probability that the service time distributions or the service time follows negative exponential distribution. Okay. And I'll explain this as well. Erlang distribution. Okay. So service time, what does they do? They follow negative exponential distribution. Now, let it be some g of t, already f of t I have considered. Probability that service time is t minutes. Service time is t minutes. Okay. So what happens is this is equal to mu e power minus mu t. Mu is also mean only, we know. Mu usually used as mean only. Okay. So t ranges from 0 to infinity. Mu is the mean service rate. Please remember this. Mean service rate. Please remember this. What is lambda? Lambda is the mean arrival rate. I can just write here mean, and these decide arrival rate. This finally decide the what's the